Hello and welcome to Vodcast 2.1a on motion. This is the introductory vodcast for the largest unit in the DP physics course. And we'll start by really doing a bit of an introduction. Science is based on observation. Observation came first. All conjecture, all predictions, all hypotheses, all models, all theories, all laws, all of this comes afterwards. And a basic observation is movement. Things move. Our universe consists of change. On every scale, from the nanoscales up to galactic clusters, things are moving. Conceptually, movement is a very big idea. It ties in the ideas of forces, which are needed to pushes and pulls to make things accelerate, to start them moving, to stop them moving, to change their direction. It incorporates the idea of energy that's needed in order to give those forces, and the volumes in which those forces act, fields. All of these are really big ideas, but at their heart, they're based around movement. And if we want, in order to model and make predictions, we need to be able to write down equations in physics and draw graphs which illustrate their movement. We need to be able to describe movement. And so that's what we're going to start by doing at a very basic level in this course. Many things move, everything moves, but we'll start with the ball. So for example, a very simple movement is shown on this particular image. The ball moves from position A through a curving path through to position B. It leaves A at time t equals 0 and arrives at time t equals t. So we've measured position A, we've measured position B, we know the path it takes between them, and we know the time, delta t, the change in t, that it takes to do so. Now the distance travelled by the ball, also called the path length, it's a scalar quantity, it's measured in meters, and it simply is that distance. Imagine measuring it with a tape measure or some other measuring device. That will give you the distance travelled. Displacement is a bit like distance, but it's a vector quantity. It's the distance travelled in a particular direction in a straight line. It's literally how can you get from A to B by the straightest line, probably the shortest time possible. It's a vector quantity, it has a length and a direction, and like distance, the unit is the meter. The symbol, by the way, is S. Remember, symbols for quantities should be given in Times New Roman font and italics. Italics times New Roman font. Okay, if you want to make yours look particularly good. So D for distance, S for displacement. Now, sometimes these two quantities are very similar. For example, if you have a straight path, then the displacement equals the distance. Same as. Okay, the displacement has additionally the direction, if you want to describe it, but basically they're the same thing. However, a closed loop, as is shown on the right here we have a circular closed loop, but it could be any shape. Think about any running track or Formula 1 circuit or anything like that. If you complete one entire lap, then your displacement is 0 because you're back where you came from. The distance, the displacement between B and A is 0 because they're both the same place. Okay, so that's displacement and distance. And moving on, we have the other piece of information. Remember, we measured time. Time started at 0 and finished at t, delta t, the time taken. Well, if we include that information, we can calculate speed. Now, speed is a scalar quantity. It is simply the distance travelled per unit time. So if I want to know the speed of my ball between A and B, I will need to know the exact distance travelled, the path length, and I will divide that by the time taken, which will give me speed equals d over delta t. Now, that would assume, if I assume that ball travels at a constant speed, no problems. But journeys don't often happen at constant speeds. Instead, the speed starts, it changes, it goes up, it goes down. Which leads us to two values, the average speed and the instantaneous speed. The average speed section is simply the complete distance travelled, measured for example by a tape measure, divided by the overall time taken. Okay, it averages out the fast bits and the slow bits. It just says this is the total distance travelled and this was the time it took. Divide one by the other to give you the average speed. You could do the average speed for the whole journey, or you could do the average speed for a section of a journey. The instantaneous speed, on the other hand, is the speed that the object is travelling at any particular moment in time. Now, 10 seconds after the start, at one particular moment. And that can be measured directly, or sort of directly, using a speedometer, or possibly using a GPS or something like that. But that will give you the instantaneous speed. So if you think about the last journey you took by car or by bus, then you could calculate the average speed if you carefully measured your path and you divided by the time taken. But you could also know the instantaneous speed at any point if you looked at the speedometer of the vehicle. Velocity is a similar concept, but is based on displacement instead of time. Now, there are some situations where this can give you some funny results. Remember the closed path that I mentioned earlier? There you go. Suppose I wanted to calculate the average velocity of a runner going around a track. Well, that was actually pretty easy. Over the course of the entire race, assuming they start and stop at the same point, then the displacement is zero, and velocity is displacement divided by time, so 0 divided by anything is 0, so the velocity will be 0. So the average velocity of a Formula 1 car during a race is 0. Of course, the average speed is not 0. You do have to be careful about these different ideas. Velocity can also be average and instantaneous. So to calculate the average, you just need to know the distance between A and B measured in a straight line and the time taken. That will give you the average. You also need to indicate the direction because it is a vector quantity. The instantaneous velocity, again, a speedometer will give you that information, or a GPS, but you do need again to include the direction as it is a vector quantity. Speed is scalar, velocity is vector. Very simple. Now, talking about direction, you can indicate direction using any convention you want: north, south, east, west, 20 degrees, towards the post office, as you prefer. But often in science we'll keep things nice and simple by analysing one-dimensional motion, or at worst two-dimensional. Very rarely do we venture into 3 dimensions. One-dimensional velocity is very, very simple because you can simply use a sign to indicate direction. So you can decide that from left to right is positive, and therefore anything that goes from left to right will be given a velocity in meters per second with a plus sign. On the other hand, any velocity that goes from right to left would be negative. Again, you can decide this direction. You want to make right to left positive, you go right ahead and do that. Just be aware that if right to left is positive, then left to right will be negative. Whichever way is positive, negative is in the other direction. Now, the final thing to remember about velocity, but actually this applies equally to distance, displacement and speed, is that it really is all relative. When we say the displacement from A to B, we're saying from A. If we choose a different reference point and a different starting point, we'll have a different answer. The case of velocity is particularly apparent. Let's look at this particular picture here. We'll keep something simple. There's only got one direction, 1D movement. You're either moving from left to right, like the car, or from right to left, like the aeroplane. But still, the girl in a red dress considers herself to be stationary. And you, in sort of your hypothetical observer watching the girl, would probably mentally consider yourself to be stationary as well. So according to A, according to the girl in a red dress, the green car, B, is travelling at 20 meters per second from left to right towards her. The aeroplane C is travelling from right to left. So according to A, if we've made left to right positive, then B is travelling at 20 meters per second. C, on the other hand, is travelling in the other direction with a speed of 100 meters per second. So the airplane's velocity must be minus 100 meters per second. Positive 20 meters per second, negative 100 meters per second. But both of those values are purely compared to the stationary girl. According to B, the car can think of itself as being stationary. That's perfectly fine. It can say, hey, I'm stationary and everything else is moving around me except perhaps another car next to me which is travelling at exactly the same velocity. So according to car B, the girl is travelling at 20 meters per second, not the car. But remember, we've already defined as positive from left to right, but the girl is going to be travelling from right to left towards the car, so her velocity must be minus 20 meters per second. The aeroplane, which according to the girl was doing minus 100 meters per second, is now travelling, according to the car, at the combined velocity of minus 120 meters per second. The negative 100 meters per second observed by the girl in her frame of reference combined with the 20 meters per second that the girl would observe the car travelling at. If this gets a little bit confusing, I apologise. As an exercise, work out according to C what is happening. C imagines itself to be stationary, so what will be the velocity of A according to C, and what will be the velocity of B according to C. Okay, so I'll leave you with that exercise. Thank you very much.